Alright, so the last video ended at slide 34 for NMR spectroscopy, so we are here at slide 35, starting with alcohols and amine peaks. Okay, so alcohol and amine peaks often appear as singlets. Okay, the chemical shift will depend on the solvent used and the concentration of your sample. Okay, to verify that the signal that you're pretty sure that is an alcohol or an amine peak, you can make that signal. So if you take your sample and you stick it in a spectrometer and obtain an NMR spectrum, you'll see it. You'll identify all of your peaks, and you're pretty sure that one of them is your alcohol peak. Well, to make sure it is, you'll take your sample, add some D2O to it, shake the sample a little bit, all right, and then put your sample back in the spectrometer and get another spectrum, and you will look for the peak that disappeared. And the peak that disappeared is absolutely your OH peak. Okay, so this is because we exchanged D2O for deuterium. All right, so the deuterium is invisible in the proton NMR spectrum. So the signal will disappear. Okay, so just kind of showing what's going on here. So say we have some ethanol, okay, and we added D2O to it. You'll get exchange for hydrogen for deuterium, and then you will generate monodeutyrated water molecule. So you can do the same thing for amines as well. So here I'm going to use like a primary amine. Now, by the way, you're adding excess D2O. You just have enough. You just add a huge amount of D2O. I say huge. It's like you'd add like 1/4 of an ml or something. But since your sample concentration is so small that that's actually a huge excess, so you're adding excess D2O, but just to clarify, for primary amines, you would need at least 2 equivalents of D2O because you're going to make 2 equivalents of monodeutyrated water to get both hydrogens on your primary amine to exchange for deuterium. Okay. So that is slide 35. Slide 36, coupling constants. Okay, so coupling constant is the distance between the any 2 peaks of a multiplet. Okay. The distance is in hertz. We can use hertz because the signals, the distance between the peaks is independent of magnetic field strength, and so a 7 hertz coupling, 7 hertz wide doublet, for instance, will be 7 hertz wide in a 60 megahertz magnet or a 900 megahertz magnet. You may not be able to see the doublet in a 60 megahertz magnet because you don't have enough resolution, but you definitely see it in a 900 megahertz spectrometer. So coupling constants are independent of the strength of the external field. So multiplets with the same coupling constant. So if you have like a doublet in one part of the spectrum and a quartet in the other part of the spectrum, and they have the same coupling constant, this kind of gives clues that those 2 signals, the protons represented by those signals, may be related, may be adjacent to each other. So adjacent. And they are splitting each other. That's why their coupling constants match. Okay, so the next slide, slide 37, I don't have anything to fill in. This is just kind of, this, by the way, is in your book. Okay, I just put it here just for emphasis, but Notice this is a 2-bond coupling, so this is geminal protons. This is the only time you would see something like this is if these two protons were non-equivalent, say like they were adjacent to a chiral center or something like that. But the coupling is quite strong, so 10 to 16 hertz, that's quite strong. The only area you see a coupling that strong is over here in trans orientation vinyl protons, so 12 to 18. Free rotation, your typical alkyl 3-bond coupling is around 7-ish hertz. 2 protons that are stuck in the anti-orientation, okay, so it's 3-bond coupling, but they're stuck anti, 8 to 13 hertz. 2 protons that are stuck in gauche are 2 to 6. So I'm not going to orate all of these numbers. I mean, they're here for you to see. Just notice here is an aryl 4-bond coupling, so aryl 4-bond coupling. It's not uncommon to see these, but I'd say it'd be pretty common for them to be 3 hertz. Less than 2 hertz is what I would normally expect. I've never personally seen a 5-bond coupling. It would definitely be less than 1 hertz. But this is just information like this will not be provided to you on the test. This is for you to know. So I would definitely get comfortable with these values. Okay, so para-nitrotoluene. So para-nitrotoluene has 2 pairs of equivalent aromatic protons. And we see that because we have 2 signals here. So let's call them A and B. So we'll call these A, and we'll call these B. And I'll circle. Yeah. Okay. So these 2 protons are equivalent through symmetry. Okay. So they are one and the same. If you notice, they both are seeing 1 proton. So 1 plus 1 equals 2. That's a doublet. Okay. Now B, these 2 are also equivalent. They're equivalent through symmetry. So they are also both seeing 1 proton. So 1 plus 1 equals 2. So that's a doublet as well. Now which doublet is which? HA is closer to the electron withdrawing group. Remember that electron withdrawing groups are withdrawing electron density, and it's electron density that shields things. And so since these are more de-shielded, they are the further downfield. They are the further downfield signal. And these 2 protons are the signal. So the integration would show like 2 for that. The methyl, they are adjacent to no protons. So the closest proton is 1, 2, 3, 4 bonds away. It's typically too far for alkyl protons to see each other, and so that's why it's a singlet. The integration would show not 2. I don't know why I wrote that. Would show 3. Okay, so ortho hydrogens is approximately 8 hertz. The peaks, these 2 peaks are separated, kind of pulled away from each other by about 8 hertz. Okay, so you can also do chemical shift prediction for aryl protons. If you remember back on that slide or a few videos ago, the aryl protons, you can do the same thing. So let's go ahead and just do that real fast here. So we're using para-nitrotoluene. Okay. So we call these 2 HA, these 2 HB. So we'll just continue that here. So HA, if you notice, the base value for an aryl proton is 7.36. Okay. and they are ortho. Both of these are ortho to our nitro group. Okay, so we have to use the ortho. Ortho, HA is ortho to nitro, so we have to add 0.87 ppm. And if you notice, these HAs are meta to a methyl. Okay, so they are meta to a methyl. So subtract 0.11 ppm. And this gives us a value of 8.12. Theoretical or experimental values is 8.10. Okay, so HB, still starting with 7.36. HB is ortho to a methyl. Okay, ortho to a methyl. So we've got to subtract 0.18, and they are meta to a nitro. So add 0.2. This comes out to 7.38 ppm. Experimentally determined values is 7.31 ppm. Let's see here. Let's go ahead and do the methyl. I think some of the lectures I did the methyl, some I didn't, but I'll go ahead and put it in here. So let's just call these HC. That is a methyl, right? So the base value is 0.9 ppm. Alpha position is an arrow ring, and so if you refer to the chart on page 367 in your book, you'd see that you would have to shift downfield by 1.4 ppm for a methyl having an arrow ring at the alpha position. So that's 1.4 ppm. So that comes out to 2.3 ppm. And actual data shows 2.46. All right. So that's how you do that. That's slide 39. By the way, on the test, I will give you this information because the charts for these types of things, if you refer to page 367 in your book, you'll see that there's just a ton of values. So anything like this, I will provide you with this data on the test. Okay. So vinylic coupling, so page 40 here. Yeah, I will get through 41 and then I'll stop this video. So, go ahead. This NMR spectrum is representing this compound, okay? So if you notice, there are two vinylic protons, okay? And if you notice, they are in the cis orientation to each other, okay? So cis is around 10 hertz. You would expect to see 10 hertz. The range is somewhere between 6 and 12. 10 hertz falls within that range, and so you would expect a split about this wide. That would be normal, and you can see these two protons or these two signals were representing these two protons. Okay, and you can see the little blow up here that they are right around 10 hertz wide. Okay. The proton circled in blue is that signal. It's closer to the electron withdrawing carbonyl. The green proton is right here. All right. And these two methyls are this big peak right here. That methylene is that signal, and that methylene is that signal. And that's all for that. So I'm going to go ahead and finish this slide right here, and I'll go ahead and end this video. So time dependence. Molecules are tumbling in solution. All right. NMR is a very slow spectroscopic technique, and so we get a very large average signal. So if you can, a good example of this is like a long exposure picture. Like if you took a long exposure picture of like a football play or something like that, all of the players and everything would look very smeared. And that's because it's a long time exposure, so you get action shots will look smeared and stuff. So a good example of this, if like cyclohexane, you should expect to see separate signals for axial and equatorial hydrogens. You would expect that. But cyclohexane is flipping between all of the conformers so fast, like chair to half chair to boat, twist boat, back to half chair to the other chair, that you don't see that. You only see one signal because they're all interchanging so fast. And just a few slides ago, proton transfer on alcohol and amines, you'll just see a singlet for those because they're moving so fast. They don't stick around on any particular oxygen for long enough to see how many adjacent protons there are. So that is all of slide 41, and I will go ahead and stop this video here.